Hello everyone, welcome back to the channel. Today we are going to be talking about one of the most important macromolecules. Today we are going to be talking about lipids. Now, what are lipids? These are organic compounds that are insoluble in polar solvents but soluble in non-polar solvents like chloroform. They are hydrophobic in nature and they are commonly found in oils, butter, waxes, hormones, and vitamins. And in this video, we're going to be talking about the classification of lipids mostly. So, the different types of lipids we have fatty acids. These are the basic building blocks of virtually every other kind of lipid, as we are going to see. We have triglycerides and waxes, which are important for energy storage and protection. We have glycerophospholipids, which are a vital component of cell membranes. Sphingolipids are also another vital component of cell membranes, and cholesterol, which is a precursor for steroid hormones and bile acids. So we'll be starting off with fatty acids. Now, the structure for fatty acid consists of a carboxylic group attached to a long hydrocarbon chain, and we could have saturated fatty acids. We also have unsaturated fatty acids. The saturated fatty acids are devoid of double bonds, so they form a linear chain and they are typically solid at room temperature, just like butter. So you can see the structure of a saturated hydrocarbon. This is basic chemistry, anyways. And unsaturated fats contain one or more double bonds and they tend to feature a bend in their chain. They are typically lipids at room temperature, just like groundnut oil, olive oil, and whatever cooking oil you can think of. So this is structure of how the double bond looks like. So here we see a typical example of a saturated fatty acid, like stearic acid, which has 18 carbons. So this is your carboxylic group and your long hydrocarbon chain. Now, under unsaturated fatty acids, they may be cis configuration or trans configuration. In the cis configuration, the hydrogen bonded to the two carbons where the double bond occur are both on the same side. So you can see the two hydrogen groups on the same side. Whereas in the trans configuration, the hydrogen groups bonded to the carbon wherein the double bond occurs are at opposite sides of the structure. So oleic acid is another 18 carbon fatty acid, but we have the cis oleic acid which has this bend due to the nature of this cis configuration in the middle, and we have trans which doesn't have as much a bend. This bend is known as a kink. Now, in nature, fatty acids are mostly found in esterified form rather than free. To be esterified means to be in combination with another moiety. So they could be in diacylglycerols, they could be part of triacylglycerols, they could be esterified to cholesterol and other moieties. And some common examples of fatty acids include palmitic acid, which is 16 carbon, stearic acid, which we have seen earlier is 18 carbon, oleic, linoleic acids, and so on and so forth. So here are some examples. You can see that the double bond in oleic acid occurs between carbon 9 and 10, and in linoleic acid there are two double bonds, one between 9 and 10 and another between 12 and 13. Now, the major roles of fatty acids are as a source of energy and building blocks. The source of energy because it breaks down to release more energy than carbohydrates in the cell due to its larger structure. It serves as a long lasting fuel reserve for the body, and they act as building blocks because they are used to make larger lipids. The next group of lipids we are going to look at are the triglycerides and waxes. Now, triglycerides are composed of glycerol and three fatty acids. So, remember the fatty acids we've just finished talking about. Imagine three of them bonded to a glycerol moiety. That is your triglyceride. And waxes provide protection, a natural coating that makes leaves and skin waterproof, much like wax. The waxes consist of fatty acid and a long chain alcohol, but in basic biochemistry, we tend to focus more on triglycerides because they are metabolically more important, and that is what we're going to do. So, this is how your triglycerides are made. This is the structure for glycerol. It is carbon, a three carbon structure. So by the time you add three fatty acids, this is one fatty acid, this is another fatty acid, and this is another fatty acid. The arrow is just your alkyl group. So this is your carboxylic group attached to your alkyl group. So by the time these three fatty acids um, hydrolyze with your glycerol, you have your triglyceride. The OH here and the hydrogen here come together to release water. So that happens three times. You have three molecules of water released every time a triglyceride forms. So this is an example of a triglyceride. This is palmitic acid. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is oleic acid, and this should be alpha linoleic acid. So these are three different fatty acids combined with a glycerol backbone. It is important to know structures like this. So next we move to glycerophospholipids and sphingolipids, both of which are part of the membrane. So we also classify both of them together as membrane lipids. Now these have an amphipathic structure with a hydrophilic head and a hydrophobic tail, enabling them to create a bilayer structure of cell membranes. There is another video on the channel specifically talking about cell membranes in a lot more detail. But for the sake of staying on theme with this video, we're just going to talk about the structures of glycerophospholipids and sphingolipids. So starting off with glycerophospholipids, it has a glycerol backbone just like triglycerides, but instead of three fatty acids, it has two fatty acid tails and a phosphate group attached to a polar hydrophilic head that faces water. Whereas sphingolipids consist of a sphingosine backbone rather than glycerol backbone with just one fatty acid and a polar head. So we're going to look at the differences now. So as we have just said, this is the glycerol backbone with one fatty acid moiety, two fatty acid moieties, and then a phosphate group attached to a polar group. So this X is the polar group, this is the phosphate group, and then your two fatty acids. So this is the basic structure of glycerol phospholipids. Now, depending on what this X is, we give the name of the phospholipid. So if this X is just hydrogen, the name of that glycerophospholipid would be called phosphatidic acid. And if it is an ethylenamine moiety attached here as X, it would be phosphatidyl ethylenamine. If it is choline, phosphatidyl choline, and so on and so forth. So this is just what the structure looks like in 3D. So you have your glycerol again, your two fatty acids. This is choline, CH2, CH2N, CH3 in bracket N. You can see that it's the same structure here. So all of this part makes up the polar head that is on the outside of the cell membrane, and then the hydrophobic tail is on the inside of the cell membrane. Like I said, you might want to check out the video on cell membrane to have a better understanding of the relevance of this structure. Now we'll go on to sphingolipids, which are built on a sphingosine backbone rather than glycerol. So this is the structure for sphingosine, but as a backbone, it would have a group replacing the hydrogen atom here and a fatty acid moiety replacing the hydrogen atom here. An important example is sphingomyelin, which has your sphingosine backbone, which you can see here in black. This is the sphingosine, attached to a phosphocholine head group. So phosphate and choline attached together. So phosphocholine head group makes up this arrow that you are seeing here. This arrow is all of this, and then your fatty acid, that is this in red. So this is palmitic acid. Palmitic acid has 16 carbon atoms. It's a 16 carbon fatty acid. You can confirm this is 14, 15, 16, 16 carbon attached to this NH group. So this is the most common sphingolipid. So depending on what this arrow group is, will depend on the name of your sphingolipid. So if it is just hydrogen, that is ceramide. If it is phosphocholine, as we've seen, is sphingomyelin. When it is lactose, it is lactosyl ceramide. When it is an oligosaccharide, we call that a ganglioside, and so on and so forth. The major role of membrane lipids for building the cell membrane, because they tend to form stable and flexible barrier that separates the cell from surroundings, and they also regulate movement of substances into and out of the cell. Now we'll move on to the last group of lipids, cholesterol. Now this is the most abundant sterol in animals, because you don't see or you hardly see cholesterol in plants. It is a rigid fused ring structure with hydroxy group, which make it weakly amphipathic and critical in maintaining membrane balance and fluidity. So this particular structure, the structure of cholesterol, you find it abundant in the cell membrane. You're also going to learn a little more about cholesterol in the video for cell membrane, and it serves as a precursor for a number of hormones such as testosterone, estrogen. It is also a precursor for bile acids that help in biliary excretion. Now we'll go on to lipoproteins, which is not exactly a class of lipids, but is used in the transportation of lipids in the body. Now these are spherical particles composed of lipids and proteins, hence the name lipolipid proteins. So lipid proteins. They are micelle-like particles composed of a hydrophobic core and an amphiphilic surface composed of phospholipids, cholesterols, and proteins. The proteins on the lipoproteins are known as apolipoproteins or apoproteins, whichever. And as I've said, the main function in the blood plasma is to act as a transport vehicle for for lipids, especially triglycerols and cholesterol, to various tissues and organs. Now, we have different types of lipoproteins. We have the chylomicrons, which help to transport exogenous, which are your dietary triglycerols, and cholesterol from the intestine to the tissue. So when you eat, the triglycerols you get from your food are transported from your intestine to tissues where they can elicit their function via chylomicrons. We also have low density lipoproteins LDL, intermediate density lipoproteins IDL, and very low density lipoproteins VLDL, all of which transport endogenous triglycerols and cholesterols from the liver to tissues. So the triglycerols that you produce in your body, in your liver specifically, it transports those triglycerols and cholesterol from your liver to different tissues. And finally, we have the high density lipoprotein, the HDL, which transports endogenous cholesterol from the tissues to the liver for removal. So, cholesterol that is in your tissue, the HDL would transport it to the liver specifically for excretion via the bile acid. So you can see that LDL, IDL, and VLDL tend to send triglycerols from the liver to the tissues and they can accumulate there when in excess, whereas HDL tends to take endogenous cholesterol from the tissue to the liver so that it can be removed. So that is one of the reasons HDL is seen as more beneficial compared to LDL, IDL, and VLDL in food science. Now, in summary, lipids have vital functions. They are structural components of membranes, they are the major energy storage molecules in organisms. They are precursors for hormones like testosterone and estrogen, vitamins like vitamin D, and bile salts for excretion. They are protective and insulating agents in animals such as waxes and your triglycerols. And the diversity of lipid is very crucial for its cellular structure, energy metabolism, and signaling in living organisms. So thank you for watching. I hope you learned a thing or two about lipids in this video. Please make sure you give this video a thumbs up, subscribe if you haven't already, and let me know in the comment section if you have any questions pertaining to lipids. I will see you guys next time. Bye.